How do mathematicians write crazy stuff like this? This is Let's Learn Real Analysis Part 12, and I'm going to show us how we can write something this complicated ourselves. That is, if you've been keeping up with this course. So today in class we proved lots of things that are called main limit theorems, like if an converges to A and bn converges to B, then if I multiply the sequences together, that also converges to A times B. And the hardest thing that we proved is this one up here. And so some might call it the quotient rule for limits, but it says if you have a sequence of non-zero terms that converges to a non-zero limit, then if you just did 1 over that sequence, it would converge to 1 over that limit. Now get ready, because this proof is actually pretty involved, but I want to show you a proof that I think is pretty intuitive and explain how you could really come up with this, and I'll go through the step-by-step process. The good news is the start of this process is always the same. We're going to take an arbitrary epsilon, we're going to leave a lot of space for filling in the details, and ultimately we're going to find some November so that after that point, the difference between our sequence and our supposed limit, we're going to make that arbitrarily small, less than epsilon. Now I've done some initial simplification, all with equal signs, because I can get a common denominator and simplify things with absolute value. Now this bottom expression over here, well, I know that bn is converging to b, and so that numerator I can make arbitrarily small. In fact, I could make it smaller than epsilon. But I've got to pay attention to those denominators, because that factor on the denominator of b sub n, that's changing. And even after November, it's going to keep changing. So what are we going to do? This is a good example of when we might punt in a math class. So we're going to do something and we're going to change it later, but this is going to help us see what we need to do. So because bn is converging to b, I know that I can make bn minus b in absolute value as small as I want. And so I've chosen here epsilon times the absolute value of b, that's some positive number. And when you notice, when I substitute that in over here, that factor of absolute value of b is going to cancel. And so I get this super simple looking epsilon over the absolute value of bn. Now bn is a sequence. I would love to just kind of tack an extra factor up here when I did that, but I can't do that because I can only have a number over there. That epsilon quantity has to be a number. It's not allowed to be a sequence. Have no fear, because we're going to do something really cool here. And so because our sequence bn is converging to b, there's also going to be some point where I know that my terms are going to be within, say, absolute value of b over 2 of my limit. Basically what I'm saying is I'm saying that the terms are closer to b than they are to the origin, right? They're the midpoint between the limit and the origin would basically be b over 2. And I'm saying at some point all the terms are going to be closer to that limit b. Now you have to do some unraveling here, and this would be a good place to get your pen and paper out. But basically this is going to guarantee that bn is greater than absolute value of b over 2 in absolute value for this n in this range. And so if we take the reciprocals of both sides, that's going to flip the inequality. We see that 1 over bn, absolute value, is going to be strictly less than 2 over the absolute value of b. Now substitute all this down here, and once I simplify, I get epsilon times 2 over the absolute value of b. Not too bad, but not the epsilon we were hoping for. However, this is where we can look back and say, you know, all that red stuff we did earlier, rather than have that be less than epsilon times absolute value of b, why don't I just change that to something different so that it will gel and work with the stuff that we've done in blue later? So now here's everything we need. We have updated this so that now at the very, very end, when everything gets canceled, I get an epsilon. And I've successfully shown that there is some point in time after which the difference between 1 over b sub n and 1 over b is going to be smaller than epsilon. Now if you're watching these videos, I'm sorry, they're going to get technical sometimes, but this is part of the beauty of real analysis, is that we can change things, we can make modifications, and ultimately that helps us have a deeper understanding of how our number system works.